Fiber optic communication starts with light, a small part of the electromagnetic spectrum that carries immense data through glass fibers thinner than hair. By controlling wavelength, dispersion, and attenuation, engineers create efficient networks that form the invisible backbone of global connectivity, turning physics into seamless worldwide communication. From high-energy gamma rays down to low-energy radio waves, the entire electromagnetic spectrum surrounds us. Each region carries unique properties and applications, from medical imaging and wireless communication to astronomy and fiber optics. Our understanding of these waves allows us to harness invisible energy across frequencies, turning natural phenomena into the foundation of modern technology and global connectivity. But in fiber optics, we work only with a narrow region, the visible and near-infrared wavelengths, where glass becomes almost perfectly transparent. Within this spectral window, light experiences minimal loss, allowing signals to travel long distances efficiently. The precision of wavelength selection in this range, typically between 850 nanometers and 1625 nanometers, enables high-speed data transmission, wavelength multiplexing, and the foundation of modern optical communication networks. The wavelength is the distance between two identical points in a wave, for example, the distance between two peaks of a light wave. It defines the color of visible light and determines how light interacts with materials. In fiber optics, controlling wavelength is crucial, as each specific wavelength can carry independent data streams, enabling multiplexing and efficient communication across vast global networks. It directly determines the wave's frequency. The longer the wavelength, the lower the frequency, and consequently, the lower the photon energy. This fundamental relationship links light's color, speed, and energy, shaping how different wavelengths behave in optical fibers. Understanding it allows engineers to choose optimal transmission windows where photons travel efficiently with minimal loss, forming the basis of high-speed communication systems. According to ITU-T standards, three main wavelength bands are used in fiber optics: 850 nanometers for multimode fibers in short-range links, 1,310 nanometers for single-mode fibers in metro networks with low dispersion and approximately 0.35 decibels per kilometer loss, and 1,550 nanometers for long-haul links with minimum attenuation near 0.2 decibels km. These are called optical windows, where glass shows minimal absorption and scattering. Below about 1,000 nanometers, molecular scattering in the glass increases dramatically, causing higher signal loss. Beyond 1,600 nanometers, absorption by hydroxyl ions also rises steeply, further limiting transmission efficiency. As a result, the 1,310 nanometers and 1,550 nanometers wavelength bands stand out as the most efficient and widely used regions for optical data transmission, balancing minimal attenuation with optimal dispersion characteristics. Passive optical networks PON use multiple wavelengths on a single fiber. Specific wavelengths carry downstream traffic from the OLT to the ONT, while others handle upstream traffic in the reverse direction. This separation enables full duplex, high-capacity communication without active components in the distribution network. PON systems use specific wavelengths for two-way data flow. GPONG 984, 1,490 nanometers downstream, 1,310 nanometers upstream, 1,550 nanometers for video. XGS PON 10G, 1,577 nanometers downstream, 1,270 nanometers upstream. NGPO NTG 0.989, 1596 to 1,600 nanometers downstream, 1524 to 1,544 nanometers upstream, using time plus wavelength multiplexing to boost capacity. This technique underpins WDM-PON wavelength division multiplexing passive optical network, enabling multiple dedicated wavelength channels on a single fiber. It supports 10-bit S and higher speeds, allowing each user or service to operate on its own wavelength while sharing the same optical infrastructure efficiently. When a live network needs to be tested without interrupting service, engineers use wavelengths outside the normal transmission bands. The most common is 1,625 nanometers, sometimes 1,650 nanometers, reserved for OTDR testing and continuous monitoring. Special WDM filters inject this wavelength into the fiber so technicians can evaluate fiber health while data traffic remains untouched, a key method in GPO and FTTH maintenance today. The electromagnetic spectrum may seem vast, yet only a handful of wavelengths minus 1,310, 1490, 1550, and 1625 nanometers carry the information that drives modern communication. Understanding these precise optical windows allows us to design efficient networks, minimize signal loss, and preserve quality even across hundreds of kilometers.